What if the past is not gone, but still exists somewhere in the structure of the universe? Modern physics suggests that time may be stranger than it feels, woven together with space, light, memory, and cause. Yet even if yesterday still has a place in reality, the path back to it may remain forever closed. In this documentary, the journey moves through relativity, old starlight, entropy, and the limits of causality to understand why the past can be seen, remembered, and measured, but not entered again. Please like this video and subscribe to the channel for more calm journeys through the deepest questions of the universe. Time begins at the surface of ordinary life as a quiet arrangement of change. A shadow moves across a wall, a cup of tea cools on a table, a face grows older in a photograph. A clock does not create time, but it gives a regular sign of change, dividing movement into small parts that can be counted. In daily experience, time appears simple because it is tied to familiar things. Morning light grows stronger, footsteps cross a room, food warms and then cools, rain falls and leaves damp marks behind. Each event seems to take its place after another, and the mind accepts this order without strain. The past is the region of finished events. The present is the narrow place where change is being noticed. The future is the region that has not yet left marks. This simple picture is not the deepest account of time, yet it is the outer layer from which the larger problem begins. Human life meets time through memory and expectation. Memory is a physical process in the brain, built from changes in nerve cells and chemical connections. It does not send a person backward. It holds a trace made by earlier experience. A remembered sound, road, room, or face is not the earlier event itself. It is a present pattern shaped by what has already happened. This makes the past feel close, almost reachable, because records can be vivid. A written page carries words from an earlier hand. A stone step carries worn marks from many feet. A photograph preserves light that once came from a scene. These traces are real, but they are not doors. They are present objects whose structure was changed by past events. They show that the past leaves evidence, while also showing that evidence and return are not the same thing. The everyday sense of time is also shaped by irreversibility. Some changes can be partly undone, but many cannot be reversed in the same complete way. A broken egg can be cooked, mixed, and eaten, but it does not gather itself back into a whole shell. Smoke spreads through air and does not naturally collect into a thin line again. Ink disperses in water and does not easily return to its first drop. These examples are ordinary, but they point toward a deep physical rule. Large collections of particles tend to move from more ordered arrangements toward less ordered arrangements. The details are complex, yet the visible result is simple. Time in daily life has a direction because change leaves the world differently arranged. The direction is not merely a feeling, it appears in heat, mixing, aging, weathering, and the formation of records. Clocks give this direction a measured form. A pendulum swings, a quartz crystal vibrates, an atomic clock counts regular changes in atoms. Each clock relies on a process that repeats in a stable way. The clock does not explain why yesterday cannot be entered again. It only marks intervals between events. Still, clocks are important because they show that time can be treated as part of nature rather than only part of thought. A second is not a mood or an image. It is defined by a regular physical rhythm. When many clocks agree, communities can coordinate movement, work, travel, and observation. The agreement feels ordinary, but it depends on the stable behavior of matter. Even at this surface level, Time is not separate from the physical world. It is read through change in physical systems. The present moment feels special because awareness is limited to it. The mind cannot experience all events at once. It receives signals from the body and surroundings, organizes them, and places them within a short span. This gives the impression of a moving present, a thin edge passing from future into past. Science can describe parts of this experience through brain activity, attention, and memory formation. It does not need to deny that the present feels real. It only separates the feeling from the larger question of whether past events still exist in some deeper structure. A person may feel the past has vanished because direct access to it is gone. Physics must be more careful. Lost access is not the same as non-existence, and existence is not the same as reachability. Ordinary language often treats time as a river, but this image has limits. A river moves through a landscape, while time is not seen moving through another background. Change is what makes time visible. Without change, no clock ticks, no memory forms, no motion begins or ends. Some philosophers and physicists describe time as what clocks measure, but this is a practical description rather than a final answer. A clock is itself part of the universe, and its measurement depends on motion, energy, and matter. The surface problem is therefore gentle but deep. Time is familiar because every life is arranged by it, yet it becomes difficult when examined closely. It is known through effects, not touched as an object. The idea of travelling to the past begins from a confusion between remembering and returning. In ordinary life, a person can revisit a place, rebuild a house, restore a painting, or read an old letter. These acts bring present matter into relation with the past traces. They do not place the traveller inside the earlier event. A restored room is still a current room. A repeated journey is still a new journey. The earlier afternoon, with every grain of dust, every breath of air, every exact position of every atom, is not simply waiting in the same way that a distant city waits. Distance can be crossed by moving through space. Past time is not available by ordinary motion through streets, fields, oceans, or sky. The difference is quiet but decisive. Daily experience also teaches that causes appear before their effects. A hand pushes a glass, and the glass moves. Fire heats water, and the water warms. A seed grows after being planted. In ordinary settings, this order is so dependable that it becomes almost invisible. It supports memory, responsibility, evidence, and explanation. When someone studies the past, the method depends on effects that remain after causes have acted. Tree rings, ice layers, bones, ruins, and written records all work because later states carry signs of earlier states. If past travel allowed direct interference with earlier causes, the ordinary structure of explanation would be disturbed. At this outer level, the issue is not yet a mathematical contradiction. It is the first recognition that the past has a protected role in how events make sense. The surface layer of the topic therefore contains both invitation and restraint. The past feels present through memory and record. It surrounds the living world as marks, habits, landscapes, and inherited matter. Every object carries a history in its shape. Every body contains atoms that have passed through stars, air, water, rock, and earlier life. In this calm sense, the past still exists as structure within the present. It is not a blank nothing. It is written into the world. Yet this kind of existence does not open a path for return. The trace remains, while the event itself is not approached by walking backward through ordinary space. The first boundary is the difference between a mark and a place, between evidence and access. between remembering an earlier world and entering it again. Beyond ordinary experience, time widens into the cosmic frame described by relativity. In this wider view, time is not simply a universal background shared in the same way by every observer. It is joined with space in a single structure called space-time, a term that means the combined arena in which events have both positions and times. An event is not only something that happens, it is something that happens somewhere and sometime. A flash of lightning, the fall of a stone, the birth of a star, and the ticking of a clock all have locations in space and positions in time. Relativity begins by treating these positions with greater care than everyday life requires. It shows that different observers can disagree about measurements of time and distance, while still agreeing on the deeper order of physical law. This change begins with light. Experiments and observations show that light in empty space travels at the same speed for all observers, no matter how they move. This result is unlike the motion of familiar objects. A thrown ball can seem faster or slower depending on the motion of the person watching it. Light does not follow that simple pattern. Because the speed of a light stays fixed, measurements of time and space must adjust. A moving clock can be measured as ticking more slowly compared with a clock at rest relative to the observer. A moving length can be measured as shorter along the direction of motion. These effects are not flaws in the clock or mistakes of perception. They are part of the geometry of space-time. The adjustment is small at common speeds. A walking person, a car, a train, and even a jet plane move too slowly for the effect to be noticed without very precise instruments. Near the speed of light, the effect becomes large. Particles produced high in Earth's atmosphere can survive long enough to reach the ground because time for them is measured differently from time for observers on Earth. Precision clocks carried on fast aircraft and satellites show measurable differences from clocks left on the ground. Modern navigation systems must account for these differences. This means relativity is not only an abstract idea, it is part of the working physical world, quietly present in instruments that depend on accurate timing. In the cosmic frame, there is no single universal clock that all of nature follows in the same way. Two events that appear simultaneous to one observer may not appear simultaneous to another observer moving differently. Simultaneous means occurring at the same time, but relativity shows that this sameness depends on the observer's state of motion when the events are separated by distance. This does not make time imaginary. It makes time relational. The order of some events can depend on viewpoint when no signal travelling at or below the speed of light can connect them. Other events keep a fixed order for everyone because one can influence the other. A cause that sends a signal to an effect remains before that effect in every valid frame of reference. This is one of the first important limits on past travel. Relativity makes time flexible, but it does not turn flexibility into free movement in every direction. Clocks can disagree. Duration can stretch or shrink depending on motion. The present can be sliced differently across distant space. Yet the paths of objects still point forward along their own time. Each object carries what is called proper time, meaning the time measured by a clock moving with that object, a spacecraft, a planet, a human body, and a particle each follow a path through space-time and accumulate proper time along that path. The amount can differ from another path, but it does not normally run backward for the object itself. The wider universe deepens this picture through gravity. General relativity describes gravity not as a simple force pulling through empty space, but as the curvature of space-time caused by mass and energy. Curvature means the shape of space-time is changed so that objects follow paths that appear as gravitational motion. Earth moves around the Sun because the Sun's mass shapes the space-time around it. A falling stone follows a path through curved space-time near Earth. Light also follows this curvature, bending near massive objects. In this view, time is affected by gravity as well as motion. A clock closer to a massive body ticks more slowly compared with a clock farther away, when the two are compared carefully. This gravitational time difference is measured on Earth. A clock at sea level ticks slightly more slowly than a clock on a mountain, because the clock lower down is deeper in Earth's gravitational field. The difference is tiny for human senses, but it is real. Around compact objects such as neutron stars and black holes, gravitational effects become far stronger. A black hole is a region where gravity is so intense that within a boundary called the event horizon, signals cannot escape outward. Near such regions, time measured by distant observers can appear strongly slowed. This slowing is often imagined as a door to the past, but that image is misleading. Strong gravity changes the rate at which time passes between observers. It does not by itself create a practical route into an earlier event. Relativity therefore loosens the everyday idea of time without breaking cause and effect. It allows a form of travel into the future. A traveller moving very fast or spending time near strong gravity can age less than people who remain in a different condition. When the traveller returns, more time may have passed elsewhere. This is not fantasy within the theory. It is a direct consequence of measured time dilation, where dilation means stretching of measured duration. Yet the traveller's own clock still moves forward. Heartbeats, thoughts, chemical reactions, and machine cycles still occur in sequence. The traveller does not pass into yesterday. The traveller passes through a different amount of time than others. This distinction is calm but essential. Relativity shows that the rate of time is not fixed for all observers, but it does not show that a person can choose a past date as a destination. The cosmic frame is more flexible than the household clock, yet it remains governed by mathematical structure. Events are connected by light, motion, gravity, and causal paths. Some separations cannot be crossed because no influence can travel faster than light. Some orders are protected because cause must remain before effect along any possible signal path. The universe is not arranged like a hallway with yesterday behind one door and tomorrow behind another. It is a space-time structure in which each object follows its own continuous path. At this second layer, the past becomes less like a vanished stage and more like part of a four-dimensional pattern. Four-dimensional here means 3 dimensions of space joined with 1 dimension of time. The pattern may contain events that ordinary experience calls past, present, and future, depending on the observer's path. This idea can make the past seem more real than daily intuition allows. Still, reality within a structure is not the same as access within that structure. A mountain may exist across an ocean, and a spacecraft may cross space toward a planet. But a past event is not distant in space alone. It is separated along time, inside the geometry that also preserves causal order. Relativity opens the universe outward and makes time more subtle, while keeping the first boundary in place. From the wider cosmic frame, the next layer is the light that crosses distance. Light makes the universe visible, and it also makes the past visible. The sun is not seen exactly as it is at the instant of observation. It is seen by light that has taken about 8 minutes to reach Earth. The moon is seen by light that has crossed the space between the moon and Earth in a little more than 1 second. The stars are seen by light that may have travelled for years, centuries, or far longer. This does not require imagination or special instruments to begin. Every night sky is already a view into earlier events, because sight depends on signals that need time to arrive. distance turns vision into history. This history is not the same as travel. A telescope gathers old light, but it does not carry the observer to the old place or old moment. The light that reaches the telescope is a physical messenger from an earlier event. It has moved through space along a path allowed by nature. It brings information about the temperature, motion, composition, and brightness of the object that emitted or reflected it. It does not bring the object itself into the present. It does not open the earlier scene so that matter from the present can step into it. The difference is quiet and important. Looking at the past is possible because the past sends traces forward. Entering the past would require present matter to move against the normal direction of causal connection. Astronomy depends on this difference. When astronomers observe a nearby planet, they study sunlight reflected from its surface after a delay. When they observe a distant nebula, they study light that may have crossed great regions of interstellar space. When they observe a galaxy millions or billions of light years away, they see it as it was when that light began its journey. A light year is a measure of distance, not time by itself. It means the distance light travels in 1 year in empty space. Because light has a finite speed, a faraway object is never seen in its immediate present. The universe presents itself through layers of delayed information, with nearer things seen more recently and farther things seen more deeply in the past. The most distant light studied in detail comes from the early universe. The cosmic microwave background is a faint glow left from a time when the universe became transparent to light. Before that stage, matter and radiation were tightly coupled, and light could not travel freely over vast distances. After the universe cooled enough for atoms to form, light began moving through space in a freer way. That ancient light is now stretched by the expansion of the universe into microwave wavelengths. It does not show the first instant of everything, and it does not show a place outside the universe. It shows an early state from which light has been travelling for most of cosmic history. It is one of the clearest examples of seeing an earlier layer without returning to it. This kind of observation can feel close to time travel because it reveals what no longer exists in the same form. A star seen from Earth may have changed greatly since its light began the journey. A distant galaxy may have merged with another galaxy, formed new stars, or grown quieter. The image in the telescope is not false. It is accurate for the light that arrives. It records the object at the time the light departed. The delay is not a flaw in vision. It is the condition that makes cosmic history observable. The farther the light travels, the older the visible information becomes. In this way, nature gives astronomy a layered archive, written not on paper, but in photons, the small packets of light and electromagnetic radiation. Photons carry information because their properties are shaped by the source and the journey. Their wavelengths can reveal chemical elements through patterns of absorption and emission. Their direction can show where an object lies in the sky. Their polarization, a property related to the orientation of light waves, can give clues about magnetic fields and scattering. Their redshift can show the stretching of light from cosmic expansion or motion away from the observer. Each property is a present measurement of an arriving signal. The past is not opened as a place. It is inferred from the signal structure. The telescope does not reverse time. It receives what time has allowed to move forward. The finite speed of light also protects causality in ordinary space-time. Information cannot arrive from an event before a signal has had time to travel. A flash from a star reaches surrounding regions in expanding shells of light. Only after the shell reaches a place can that place be influenced by the flash. This creates what physicists call a light cone, a term for the set of directions in space-time that light can connect from an event. The future light cone contains events that can be reached by signals from the event. The past light cone contains events whose signals can reach it. Events outside these cones are too far away in space and too close in time to be connected by light or any slower influence. This structure gives the universe an order deeper than ordinary timing. Within this order, the observer is always receiving from the past light cone. Everything seen, heard, or measured comes from events that occurred earlier, even if only by a tiny fraction of a second. A hand is seen after light leaves the skin and enters the eye. A sound is heard after waves move through air. A scientific instrument records a particle after that particle reaches a detector. Direct experience is always slightly delayed for nearby things. The delay is too small to matter in daily life. For the cosmos, the delay becomes enormous. The principle remains the same. Observation is built from incoming traces, not from direct possession of the present state of distant things. This makes the universe rich in records. A supernova remnant carries expanding debris from a stellar explosion. A planet's surface carries craters made by impacts long past. A galaxy's shape carries signs of gravitational encounters. Light from each of these records adds another layer. The past exists in astronomy as arriving radiation and present structure. It can be measured with patience and care. It can be compared with models of matter, gravity, nuclear reactions, and cosmic expansion. The result is not a story invented around darkness. It is a scientific reconstruction grounded in signals. Yet every part of this reconstruction depends on information travelling forward from earlier states to later observers. The wish to travel to the past often begins with the truth that the past is visible. If a telescope can show a galaxy as it was long ago, it may seem that old time is still somewhere to be reached. But the telescope's view is not a location in the same sense as a shore across water. The old light has already left that galaxy. The image forms here, now, when the light meets the instrument. A traveller moving toward the galaxy would meet later regions of space-time along the path, not the departure moment of the light already received. Motion through space cannot catch the past state once its signals have moved on and the source has changed. This layer of the topic is therefore clear and gentle. The universe does allow looking back. It allows the study of earlier stars, earlier galaxies, and earlier cosmic conditions. It allows present instruments to receive ancient light and build knowledge from it. It does not allow the same process to become entry into earlier events. Light is a record moving outward, not a road moving inward against time. Its journey preserves the order between source and observer. The past remains present as information, carried across space by signals that arrive after their causes. The observer can gather those signals, compare them, and learn from them, while remaining on a forward path through space-time. Inside the light-bound universe, relativity gives time a measured flexibility. This flexibility is often the first place where the idea of travelling through time seems to gain scientific shape. A clock can tick at a different rate because of motion. A clock can tick at a different rate because of gravity. These statements are not guesses. They belong to tested physics, yet their meaning is careful and limited. A slower clock does not become a backward clock. A stretched duration does not become a reverse sequence. Relativity changes how much time passes along different paths, but each ordinary object still experiences its own changes in order. The body ages from one heartbeat to the next. A machine wears from one cycle to the next. A particle decays after existing for a measurable interval. Time bends in rate, not in the simple direction of lived process. Motion is the easier part to picture. When one observer moves very fast relative to another, each can measure the other's clock as slowed in a precise way. This effect is called time dilation, meaning a stretching of measured time between frames of reference. It does not arise because the moving clock is poorly made. A perfect clock would show the same result. The change comes from the structure required when the speed of light remains the same for all observers. Space and time share the adjustment. What one observer counts as a distance and a duration can differ from what another observer counts. While the laws of physics remain consistent, the result is subtle, but it has been confirmed in particles, atomic clocks, and satellite systems. This flexibility allows one path through space-time to contain less elapsed time than another. A traveller moving at extremely high speed and then returning can be younger than someone who stayed behind. The traveller has not escaped time. The traveller has simply followed a path with less proper time, the time measured by a clock travelling with that person. Every chemical reaction in the traveller's body still proceeds forward. The journey does not carry the traveller into an earlier childhood or into the earlier room that was left behind. It carries the traveller into a future in which more time has passed elsewhere. Relativity therefore permits an uneven passage into the future. It does not, by motion alone, permit a return into the past. Gravity creates a second kind of unevenness. A clock deeper in a gravitational field ticks more slowly compared with a clock farther away. Near Earth, this difference is small but measurable. Precision timing must account for it because satellites orbit above the planet, where gravity is weaker and their motion is different. The practical corrections are small, yet they show that time is woven into gravity. The rate of time depends on position in the gravitational landscape. Near very dense objects, such as neutron stars or black holes, this effect becomes much stronger. A distant observer may describe a clock near a black hole as extremely slowed. The clock itself, however, still moves through its own sequence. It does not witness its own time stop or reverse. A black hole gives this distinction strong emotional force, but the science remains steady. The event horizon is the boundary inside which signals cannot escape to faraway observers. Time near this boundary appears strange when described from outside. Light climbing away loses energy. Clock seems slowed, and falling objects appear increasingly delayed in the distant view. For the falling object itself, the local passage of time continues. A clock falls. A body falls. Local processes remain ordered. The experience does not become a visit to an earlier universe. The event horizon changes communication and geometry. It does not create a simple doorway to past events outside it. The mathematics of relativity allows space-time to have many possible shapes. Some solutions to the equations are simple and match observed conditions well, such as the space-time around ordinary stars and planets. Other solutions are more exotic. They may describe rotating universes, idealized cylinders, or paths that curve through time in unusual ways. A solution in mathematics is not automatically a physical machine. It must also be connected to realistic matter, stable conditions, and the known behavior of energy. The existence of a mathematical form does not prove that nature builds it, or that it can be made by technology. Relativity is generous in possible geometries, but the actual universe appears more constrained. The flexibility of time also does not remove the speed limit set by light. Massive objects cannot be accelerated to the speed of light by any known process, because the energy required grows without bound as that limit is approached. Light itself follows paths that define the boundary for causal influence. Signals moving slower than light remain inside that boundary. A person, spacecraft, or message cannot simply move faster than light and loop into an earlier event under ordinary conditions. Some imagined shortcuts try to avoid this by changing space-time itself rather than moving through space faster than light. At this layer, however, the important fact is simpler. Relativity bends the measure of time but protects the local forward path of matter and information. The phrase time travel often hides two very different ideas. Travel to the future can mean taking a path on which less time passes for the traveller than for others. This is allowed in relativity and observed in small forms. Travel to the past means arriving at an event that lies before departure in the traveller's own causal history. This is far more difficult. It threatens the ordering that makes physical explanation stable. Relativity does not forbid every unusual spacetime in its equations. But ordinary time dilation is not enough to cross that boundary. It can separate ages. It can make twins no longer the same age after different journeys. It cannot place the younger twin into the earlier room before the journey began. At human scales, these effects remain modest. Aircraft flights change elapsed time by tiny amounts. Satellites require timing corrections measured with great precision. Particles in accelerators can live longer, as measured by the laboratory, because they move so quickly. These are real examples, but they are not openings into history. They show that time is less rigid than daily life suggests. They also show that the effect has a clear direction. A fast particle reaches a detector later than it would without dilation from the laboratory's view, and its own internal decay process still proceeds forward. A clock on a satellite keeps ticking, not unticking. The physical sequence remains intact. This layer therefore deepens the boundary rather than erasing it. The universe allows different amounts of time to pass along different paths. It allows clocks to disagree in ways that are not errors. It allows gravity and motion to reshape measured duration. These facts are among the great discoveries of modern physics. They make time part of the active structure of the cosmos, not a silent stage behind it. Yet they do not make the past an accessible destination. The past can be observed through delayed signals, and the future can be approached unevenly through time dilation. The direction along each ordinary world line remains forward, with causes giving rise to effects and records forming after events. Relativity bends time's rate with quiet precision, while leaving the deeper order unbroken. At the next layer inward, time is no longer treated only as a rate measured by clocks. It becomes part of a larger geometry, a shape in which events have their places. This view is often described through the idea of a block universe, a name for the interpretation that past, present, and future events all belong to one four-dimensional space-time structure. The word block is only an image. It does not mean the universe is solid like stone. It means that events can be understood as arranged within a complete space-time pattern, rather than appearing and disappearing as if only the present were real. In this view, the birth of a star, the fall of a leaf, the cooling of a planet, and the reading of a clock are all located within the same extended structure. This idea grows naturally from relativity because there is no single universal present shared by all observers. When distant events are compared, different states of motion can define different slices of simultaneity. A slice of simultaneity is a way of grouping separated events as happening at the same time from a given viewpoint. One observer's slice can tilt differently from another's. This does not disturb local experience. Nearby clocks and nearby events still form an orderly present for each observer, but across great distances, the idea of one cosmic now becomes less simple. The block universe is one way to take this seriously. It treats the full space-time arrangement as the deeper reality. While the present becomes a feature of an observer's path through it, The block universe can make the past seem as if it still exists. If all events are part of space-time, then earlier events are not simply nothing. They have positions in the structure. The first light from a young star, the formation of an ancient sea, and the motion of a long-vanished animal can be described as events with space-time coordinates. Coordinates are labels that identify where and when an event occurs. They do not create the event, and they do not make it accessible. They only allow a consistent description. A map may mark an island, but a mark on a map is not a boat. In the same way, a location in space-time is not automatically a route that an object can follow. The difference between existence in a structure and access by motion is central. In ordinary space, if a mountain exists far away, a traveller may cross the land to reach it, if no barrier prevents the journey. The mountain remains at another place in space while the traveller moves through time. A past event is different. It is not merely far away across space. It lies behind along the time direction of the traveller's own path. To reach it would not mean travelling through empty distance alone. It would require changing the relation between cause, memory, and sequence. A person standing in the present contains records of earlier events. Those records are part of the present state. Travelling to the earlier event while carrying those records would place later information inside an earlier region. In space-time geometry, objects follow paths called world lines. A world line is the path of an object through space-time, combining its movement through space with its passage through time. A person sitting still on a chair still has a world line, because the person moves through time even without changing much in space. A planet has a world line around a star. A beam of light has a light-like path, meaning it follows the boundary set by the speed of light. The block universe contains these paths as threads through the four-dimensional pattern. Each thread has an order along it. Events on the thread are not merely scattered points. They are connected by the history of the object. For ordinary matter, the world line points within the future direction defined by local light cones. A light cone at an event marks which directions in space-time can be reached by light and which can send light to that event. Matter moves more slowly than light, so its path remains inside the light cone. This condition keeps motion causal. It means a body cannot simply veer sideways into a region outside possible influence, nor can it turn backward into its own earlier state under normal conditions. The block universe may contain all events, but the allowed paths through it are not arbitrary. Geometry gives structure, and physical law gives permission. The idea of a complete spacetime pattern can be unsettling because it seems to reduce the special status of the present. Yet physics does not require ordinary awareness to vanish. An observer inside spacetime experiences events in sequence because the observer's brain, body, and instruments occupy one local region at a time along a world line. Memories are formed from earlier events on that path. Anticipations concern events not yet encountered on that path. The present is therefore local and physical. It is not necessarily a universal line across the cosmos. This is enough for experience, but it is not enough to create a passage into the past. The observer's movement through the block is not like a hand moving freely over a page. It is the observer's own existence along a constrained path. Some interpretations of physics debate whether the block universe is the best description of reality. Others defend a view in which the present has a deeper status. These debates involve philosophy as well as physics. What is widely accepted is more modest. Relativity makes universal simultaneity difficult to preserve. Spacetime descriptions work with great accuracy. Events can be represented in a four-dimensional framework. These facts do not settle every question about the nature of existence. but they do show why the past can be treated as part of the structure described by physical law. They also show why being part of a structure is not the same as being open to direct visitation. The block view also clarifies why old light is not a return path. Light from the past lies on a path that reaches the observer's present. It is part of the observer's past light cone. The earlier event and the later observation are connected in the proper order. The signal moves forward from source to receiver. A journey to the source after receiving the signal follows a different path. It cannot meet the same emission event, because that event is not waiting at a spatial position alone. It is fixed at a space-time position. The star may still occupy a similar region of space, or it may not, but the emission moment itself is not reached by later travel. At this layer, the deepest misunderstanding begins to soften. A past event may be real in a space-time description without being reachable by a machine. Reality is not the same as availability. The known laws of motion, light, and causality shape which events can influence which other events. They do not allow a body to choose any coordinate in space-time and appear there. They require a continuous path, and that path must respect local physical limits, even in a block universe. The traveller is not outside the block, selecting destinations from above. The traveller is inside it, part of it, made of matter whose own history is one of the threads. The geometry of space-time therefore gives the past a certain dignity. It is not merely an illusion left behind by memory. It can be described as part of the full arrangement of events. Ancient light, old rocks, biological inheritance, and written records all point to earlier regions of the structure. Yet the same geometry also explains the barrier. A route is not defined only by the existence of a destination. It is defined by an allowed connection between departure and arrival. Known space-time geometry allows observation of past signals and different rates of time along different paths. It does not provide ordinary matter with a path that turns into its own past. The block may contain the past, but the thread of a life still runs one way through it. Within the space-time structure, the next inward layer is the path followed by each object. This path is called a world line. A world line is the record of where an object is and when it is there, drawn through space-time rather than through space alone. A stone resting on the ground has a world line because it remains present from moment to moment. A bird crossing the sky has a world line that changes through space, while also extending through time. A planet circling a star has a long curved world line shaped by gravity. A human life has a world line made from every position of the body through every moment of its existence. The word may sound technical, but the idea is simple. Nothing made of matter appears only at one timeless point. It occupies a continuing path. This path gives travel its physical meaning. In ordinary travel, a person moves from one location to another while time passes along the person's own body. The feet step, muscles contract, nerves signal, lungs breathe, and memories form. The journey is not just a line on a map. It is a chain of physical states. The earlier state changes into the later state. The later state contains marks of what came before, such as tired muscles, remembered views, or a different position. A world line gathers all of this into one space-time description. It does not show a person outside time, choosing moments from a distance. It shows the person as a physical process extended through time. For a world line to describe ordinary matter, it must remain inside the local limits set by light. At every event on the path, light defines the fastest possible outward influence. Matter, having mass, moves more slowly than light. This means the world line of a person, planet, or spacecraft stays within the future light cone from each point along the way. It can lean through space if the object moves quickly. It can curve under gravity. It can accumulate less or more proper time compared with another path. But in known ordinary conditions, it does not tip outside the permitted region and does not turn into the past light cone of its own previous event. The path remains continuous and forward directed. Continuity matters because physical objects are not isolated labels. A person is not only a point that can be lifted and placed elsewhere. The body is a changing arrangement of matter and energy. The arrangement must pass through intermediate states. A spacecraft cannot leave Earth and arrive near another planet without existing somewhere along the route or following some allowed space-time connection. Even hypothetical shortcuts must still describe how the object's world line connects departure and arrival. A break in the path would mean the object simply disappears from one event and appears at another without a physical account. Known physics does not treat ordinary matter that way. It requires local processes and lawful connections. The order along a world line is marked by proper time. Proper time is the time measured by a clock carried along the same path as the object. It is the time that a traveller would record on a wristwatch, the time that a body would experience through aging, or the time that a particle would measure before decay, if it could carry a clock. Different world lines between similar regions can have different amounts of proper time. This is why time dilation can separate the ages of travellers. Still, proper time along an ordinary world line increases. The traveller's clock counts upward. A pulse follows a previous pulse. A thought follows earlier brain activity. The local sequence does not reverse, merely because another observer measures a different rate. This gives a quiet answer to a common image of past travel. A machine might be imagined as turning the traveller around in time, the way a boat turns around on water. But space-time does not offer time as a simple direction like north or south. To turn a world line into the past would require the future-directed path of matter to curve so far that it meets an earlier region. Such a path is called a closed, time-like curve, meaning a route through space-time that remains locally slower than light but returns to its own past. The term describes a mathematical possibility and some unusual solutions of general relativity. It does not describe an observed road through the real universe. It marks the shape of the problem. A closed time-like curve would not simply revisit a lost scene. It would place the traveller's later state among events that, in ordinary order, helped lead to that traveller's departure. The traveller would carry memories, scars, energy, and information formed after the earlier time. These later features would become present inside the earlier region. The world line would form a loop rather than an open thread. This changes the meaning of history. An event could become part of the conditions that produce itself. The path would no longer fit the simple order in which earlier states give rise to later states without circular dependence. The difficulty is not only emotional or practical, it is built into how physical explanations are arranged. World lines also clarify the difference between returning to a place and returning to a time. A traveller can go back to a childhood town because the town occupies a region of space that continues into later years. The buildings may change, the people may change, and the air and soil may change, but there is a present version of the place. The world line of the traveller can intersect the later world line of that location. This is ordinary return. The earlier version of the town is a different set of events along the town's history. To enter that version, the traveller's world line would have to intersect an earlier segment of the town's world line. Ordinary motion through space reaches the present continuation, not the earlier segment itself. The same is true for every object. An old tree has a present trunk with rings that record earlier growth. A glacier has layers from older snowfall. A cratered moon has marks from ancient impacts. These records lie along the current world lines of matter. They are reachable because they exist now as present structure. The earlier growth, snowfall, and impact events are not reached by touching the record. They are inferred from the arrangement that remains. A world line ties the record to the event in one direction, cause leaves effect. The effect can be studied later. The later study does not become a return to the cause. In physics, this directional connection is not merely a habit of thought. It is supported by the structure of signals and local interactions. A detector records a particle only after the particle reaches it. A telescope forms an image only after light enters it. A brain forms a memory only after signals alter its cells. Each process lies along world lines that meet and influence one another in permitted regions. The order may be described differently by observers moving in different ways when events are far apart and not causally connected. But when one event directly influences another, the order is protected. World lines that carry matter and information preserve the link from cause to effect. This layer therefore moves the problem inward from the shape of space-time to the path of the traveller. Even if past events belong to the structure of the universe, a traveller cannot reach them without an allowed world line. The path must remain continuous, physical, and compatible with light cones, gravity, energy, and local change. Known paths allow aging at different rates and observation of old signals. They allow return to places as they exist later. They do not show ordinary matter looping into its own earlier conditions. The traveller is not outside time looking in. The traveller is a thread within space-time, and the thread carries its own order. In that order, the past remains behind as source, trace, and record, while the path continues forward through each local moment. Deeper within the structure of space-time and the paths that objects follow lies the principle that holds these paths in a consistent order. This principle is causality, the rule that causes precede their effects in a way that allows events to be explained and predicted. Causality is not an added decoration on top of physics. It is woven into the way signals move, the way forces act, and the way information is carried. A cause is an event that can influence another event through a chain of interactions. An effect is the event that receives that influence. The connection is not abstract. It is carried by light, by fields, by particles, and by contact between matter. In ordinary life, causality appears simple. A stone is released, and it falls. A switch is pressed, and a light turns on. A flame is applied, and water warms. These examples show a sequence that is both familiar and reliable. The reliability comes from the physical laws that govern motion, energy, and interaction. The sequence comes from the fact that information travels at limited speeds. A signal must move from the cause to the effect, and that movement takes time. This gives the universe a local order. Events that are linked by signals form chains that cannot be rearranged without changing the laws that allow the signals to exist. Relativity preserves this order in a precise way. Even though different observers may disagree about the timing of distant events that cannot influence one another, they agree on the order of events that are connected by cause and effect. If one event sends a signal that reaches another event, all observers will agree that the sending occurs before the receiving. This agreement does not depend on the observer's motion or position. It depends on the structure of space-time and the limit set by the speed of light. The limit ensures that signals cannot outrun light, and therefore cannot arrive before they are sent within any valid frame of reference. This protection of order becomes critical when the idea of travelling to the past is examined. To reach an earlier event in one's own history, a traveller would need to influence conditions that, in ordinary order, helped produce the traveller. This would place the effect before the cause along at least one chain of events. For example, if an action taken after departure could alter conditions that existed before departure, the chain of explanation would no longer be one-directional. The event that is supposed to be explained would also become part of its own explanation. The clear separation between cause and effect would blur or break. The problem is not only philosophical, it is practical in the sense that physical systems rely on stable causal order. Engineering, biology, chemistry, and astronomy all depend on the assumption that causes led to effects in a consistent way. Measurements rely on signals that travel from a system to an instrument. Predictions rely on the idea that present conditions can be used to infer future conditions. If effects could act on their own causes in uncontrolled ways, these methods would lose their foundation. The world would not only be confusing, it would be unstable in a deeper sense, because the rules that allow processes to unfold would not hold in a consistent direction. In space-time terms, causality is expressed through light cones. At any event, the future light cone contains all events that can be influenced by signals from that event. The past light cone contains all events that can influence it. Events outside these cones are not causally connected because no signal can travel between them without exceeding the speed of light. This structure creates a web of permitted connections. It defines which events can affect which others. It also defines which sequences are possible. A world line that respects causality remains within the future light cone at each step. It does not cross into regions that would require signals to travel faster than light or to arrive before they depart. When a proposal suggests travel to the past, it must address this structure. It must show how a world line could be arranged so that it returns to an earlier region without violating the local speed limit or the causal order. Some mathematical solutions in general relativity describe spacetimes in which closed time-like curves exist. In these solutions, a path could, in principle, return to its starting point in time. However, these solutions often require conditions that are not known to occur in the physical universe, such as specific global arrangements of matter or energy that are not observed, or forms of matter with properties that have not been realized in usable ways. Even when the mathematics allow such curves, the physical viability remains uncertain. The uncertainty is not a small detail. It reflects the fact that causality is deeply embedded in both classical and quantum descriptions of nature. In classical physics, fields and forces propagate with finite speeds, and differential equations describe how systems evolve from initial conditions forward in time. In quantum physics, probabilities are assigned to outcomes in ways that still respect causal structure. Signals and influences do not appear to leap backward to alter earlier conditions. Quantum entanglement, a correlation between particles, does not allow controllable signals to be sent faster than light or backward in time. Observations indicate that causal order is preserved even when quantum effects are present. There are also principles proposed to protect causality. One idea suggests that the laws of physics may prevent the formation of closed time-like curves in realistic conditions, even if the equations allow them in idealized cases. This is sometimes called a form of chronology protection, meaning a safeguard against violations of time order. The details of such protection are not fully known, and the idea is still a subject of research. Observations indicate that the universe behaves in a way that maintains causal consistency. It remains uncertain whether extreme conditions could ever challenge this, but no practical method has been found to do so. At the level of information, Causality ensures that messages have a clear direction. A message is encoded in a physical system, such as a pattern of light, a sequence of electrical signals, or a written text. The encoding process occurs after the information is known to the sender. The message then travels to a receiver, where it is decoded. If messages could be sent into the past, the receiver could obtain information before it is generated by the sender. This would create loops in which information appears without a clear origin. Such loops are difficult to reconcile with the way information is created, stored, and transmitted in known physical systems. This layer shows that the barrier to past travel is not only a matter of geometry or motion, it is a matter of maintaining a consistent order of explanation. The universe allows complex interactions, delayed signals, and varying rates of time. It allows the study of ancient light and the prediction of future events. It does not show a consistent way to let effects alter their own causes without undermining the structure that makes those interactions meaningful. The calm regularity of causality is what allows science to connect events across time. It is also what prevents a traveller from stepping back into an earlier cause while carrying the results of that cause. Causality therefore acts as a quiet boundary within the deeper layers of time. It does not forbid every imaginative construction in theory, but it restricts what can occur in a physically consistent universe. The past remains connected to the present through signals that have already travelled, through records that have already formed, and through world lines that have already passed. These connections run from earlier to later. They do not form ordinary routes in the reverse direction. As the exploration moves inward, this boundary becomes more apparent. The universe can be described as a whole, with all its events in place, but the permitted connections between these events keep the order intact. Inside the boundary of causality, the next layer is the paradox. A paradox is a situation in which ordinary reasoning seems to turn against itself. In the question of past travel, paradox appears when a later event enters an earlier time and changes the conditions that allowed the later event to happen. The problem is not only that such a story feels strange, the problem is that the chain of explanation becomes unstable. If an event prevents its own cause, then it becomes unclear how the event exists. If an event creates its own cause, then it becomes unclear where the information or matter first comes from. The loop may be described in words, but words do not make it physically consistent. The most familiar kind of time travel paradox involves preventing a necessary part of one's own history. A traveller reaches an earlier time and changes something that would have led to the traveller's birth, departure, or decision to travel. If the change succeeds, then the traveller would not exist in the same way, or would not begin the journey. If the traveller does not begin the journey, then the change would not occur. The contradiction is direct. The effect removes its own cause. The loop cannot settle into a clear sequence because each step depends on another step that it also destroys. This is not simply a dramatic problem. It is a challenge to the idea that physical events have definite relations to one another. A second kind of paradox is quieter. It involves information without a clear origin. A traveller may carry a scientific idea, a design, a message, or a piece of music into the past, where it is copied and preserved until the traveller later learns it and carries it back again. The information seems to exist in a closed loop. No one creates it through discovery or invention. It is received from the future, then sent into the past, then received again. The loop is self-consistent because it does not necessarily erase its own cause, yet it raises another difficulty. Physical information normally has a history. It is encoded, copied, degraded, stored, and produced through processes that require energy and matter. A loop with no first creation leaves the origin unexplained. There is also a version involving objects. A tool, a notebook, or a small machine could be carried into the past and become the same object later carried back. If the object follows a closed path through time, its material history becomes circular. It may never be manufactured in the usual way. It may age through the loop, suffer wear, and still be required to appear in the earlier time as the object that later enters the machine. This raises questions about entropy, conservation, and identity. Matter changes through use. Paper yellows, metal corrodes, and machines lose precision. A closed loop must account for these physical changes without a beginning outside the loop. A simple story can ignore this. A physical theory cannot. Some proposed answers try to preserve consistency. One possibility is that events on a closed time-like curve must be self-consistent. This means a traveller could enter the past only in ways that already belong to history. Any attempted change that would produce a contradiction would somehow fail or would become part of the events that already occurred. In such a picture, the past is not open to alteration. The traveller's actions are included in the original pattern. The loop exists. But it does not break causality because the conditions around it allow only consistent histories. This removes the sharpest contradiction, but it does not provide evidence that such loops exist in the real universe. Self-consistency also comes with a cost. It makes freedom within the loop very restricted, at least wherever contradiction might arise. A traveller may seem able to choose, but the allowed choices must fit the already existing history. This does not necessarily violate physics, because physics often constrains what can occur. A stone released from a hand follows paths allowed by gravity and initial conditions. A chemical reaction follows paths allowed by energy and molecular structure. Yet a time loop would make the constraint unusual. The future event and the past event would have to fit each other exactly. The entire loop would need to be solved as one consistent structure, rather than as a sequence that unfolds freely from earlier conditions. Another proposed answer invokes branching histories, where an action in the past would not change the traveller's own history, but would create or enter another history. This idea is common in fiction, and some interpretations of quantum theory discuss branching in a different context. However, known physics does not provide a practical mechanism for a person to leave one history, enter an earlier time, and generate a separate world at will. Quantum theory does involve probabilities and superpositions, meaning combinations of possible states before measurement, but it does not allow macroscopic travellers to choose a past branch as a destination. The scientific status of branching interpretations is subtle, and they do not turn into a machine for past travel. The paradoxes also reveal a difference between mathematical possibility and physical process. A spacetime may be written in equations that contain closed time-like curves, but a real process must explain how the curve forms, how matter enters it, how energy behaves, how quantum fields respond, and how contradictions are avoided. It must also agree with observations. No observed system shows controllable travel into the past. No experiment has produced a message that arrives before it is sent in a way that can be used to alter its own cause. The lack of observation does not by itself prove impossibility in every imaginable theory, but it keeps the subject in the realm of unresolved and highly constrained speculation. Paradoxes are useful because they show where the strain appears. The strain is not simply in building a powerful engine or reaching a high speed. It is in preserving a coherent universe. A past traveller carries later information into an earlier region. That information can affect the conditions that make the traveller possible. Once that happens, the ordinary method of explaining events from earlier to later becomes tangled. Either contradiction appears, or strict self-consistency is imposed, or the proposal moves into unverified ideas about separate histories. Each route shows that past travel is not just difficult in engineering, it presses against the foundations of physical explanation. In ordinary science, records are stable because they form after the events they record. A fossil forms after an organism lives and dies. A photograph forms after light reaches a surface or sensor. A memory forms after experience changes the brain. These records may be incomplete or distorted, but their direction is clear. Time travel paradoxes disturb this order by allowing records or actions to appear before their sources. A book may be copied from itself. A warning may cause the danger it describes. A prevention may remove the reason for prevention. The loop becomes a knot in the chain of causes. Some knots may be logically arranged, but the known universe does not show that such knots can be made. This inner layer leaves the past even less like a destination. A destination can be reached without threatening the existence of the journey itself. A past event, if entered and changed, may threaten the conditions that lead to the traveller. If entered without change, it becomes not an open place but a fixed part of the history already present. In either case, the simple dream of stepping into yesterday and acting freely does not survive careful examination. The paradox shows that the past is not only distant in time, it is structurally tied to the present by chains of cause, record, and identity. To enter it would be to enter the roots of the traveller's own existence, where every action must either preserve the tree or undermine the branch that carries it. Below paradox, the next inward layer is the physical material that any proposed time machine would require. A path into the past is not only a pattern drawn in space-time, it must be supported by matter and energy. In general relativity, matter and energy shape space-time, and space-time guides the motion of matter and energy. A planet bends the paths of nearby objects. A star curves space-time more strongly. A black hole curves it more strongly still. If a machine is imagined as bending time into a loop, then something must create and hold that shape. The question becomes less like choosing a date, and more like asking what kind of physical substance could force space-time into such an extreme arrangement. Ordinary matter does not appear to do this. Rock, metal, water, air, plasma, planets, stars, and known forms of radiation all carry positive energy in ordinary conditions. Positive energy means that the energy measured by normal observers is above empty space rather than below it. This kind of energy curves space-time in ways that produce gravity, or pressure, or expansion under certain conditions, but it does not easily create the open loops and shortcuts often imagined for past travel. The same matter that builds planets and stars also keeps causal order stable in the conditions observed around them. It can bend paths, it can slow clocks, it can trap light inside an event horizon. It does not form a controllable road backward through history. Physicists describe some limits on matter through energy conditions. These are mathematical statements about how energy density and pressure behave in space-time. They are not simple moral rules, and they are not absolute in every quantum situation. They are tools used to express the ordinary behavior of known matter. In many classical settings, energy conditions help prevent unusual geometries such as traversable wormholes or closed time loops. Traversable means passable in both directions without being crushed or trapped. If the energy conditions hold, space-time tends to resist the shapes needed for a stable passage into the past. It may curve, but it does not open in the required way. Some theoretical paths to past travel ask for negative energy. Negative energy does not mean ordinary energy with a minus sign in a casual sense. It means a region where the energy density, measured relative to a chosen reference, is lower than the energy of empty space in a specific quantum state. Quantum field theory allows small and temporary negative energy effects in limited circumstances. One example is associated with the Casimir effect, where two very close conducting plates change the allowed quantum fluctuations between them. This does not produce a useful time machine. The effect is tiny, constrained, and balanced by the wider rules of quantum theory. It shows that nature is subtler than classical energy conditions, but it does not show that large stores of negative energy can be gathered and shaped at will. A time machine based on exotic spacetime would need more than a brief quantum dip. It would need a stable distribution of matter and energy arranged with extraordinary precision. It might need negative energy strong enough to hold open a wormhole throat, or to create a geometry where time-like paths loop back. Such requirements go far beyond known materials. No laboratory substance, no star, no planet, and no observed cosmic structure provides this in usable form. The unknown is not merely a matter of scale. It concerns whether the required state is physically permitted at all once quantum theory, gravity, stability, and conservation laws are considered together. Stability is a quiet but severe problem. Even if a mathematical spacetime contains a passage, small disturbances may destroy it. Real regions of space contain radiation, particles, gravitational waves, and quantum fluctuations. A structure delicate enough to connect times may react violently to incoming energy. Light and particles could circulate through a time loop, becoming amplified in ways that damage the geometry. Quantum fields may build up near the boundary where closed time-like curves begin. Some calculations suggest that these effects could become large enough to prevent the time machine from forming. It remains uncertain how a complete theory of quantum gravity would decide this question, but known physics gives no confidence that such structures can remain stable. The energy scale is another barrier. Gravity is weak compared with other forces at ordinary scales, so bending spacetime strongly requires enormous mass, energy, or density. Earth's gravity is enough to hold oceans and air, but the time difference between sea level and a mountaintop is very small. The sun curves space-time enough to guide planets, yet it does not loop time. Black holes create extreme curvature, but their known structure does not offer safe passage into the past. To shape space-time into a chosen time machine would require control over gravity far beyond anything known. It would require not only energy, but energy placed in forms that may not be available in nature. The issue becomes sharper when conservation is considered. Energy and momentum are not created freely. They are accounted for through local laws. Any proposed machine must say where its required energy comes from, how it is arranged, how it remains contained, and how it avoids collapse or explosion. It must also explain what happens when matter enters the region. A human body, a spacecraft, or even a signal carries energy. That energy changes the space-time it moves through, even if slightly. In extreme geometries, slight changes may matter. The traveller is not a harmless test mark on a diagram. The traveller is part of the system and can disturb the very path that is supposed to carry the journey. Known matter also obeys thermodynamic limits. Heat flows, radiation leaks, materials break, and information must be stored in physical states. A device that manipulates space-time would need to manage these ordinary processes while controlling extraordinary curvature. It would have to resist decay, noise, and uncontrolled feedback. This is not only a technological difficulty, it reflects the connection between microscopic disorder and large-scale stability. A time machine cannot be treated as a perfect symbol outside nature. It would be built, if at all, from fields and particles that fluctuate, age, radiate, and interact. There is also no evidence that the universe contains naturally occurring time machines. Astronomers observe black holes, neutron stars, galaxy clusters, gravitational lensing, cosmic expansion, and ancient radiation. These observations show powerful curvature and deep time dilation. They do not show confirmed closed time-like curves or regions where signals emerge before entering. The absence of such evidence matters because the universe has created energies and densities far beyond human engineering. If ordinary extreme astrophysical objects do not reveal usable paths into the past, then any proposed path must rely on still more unusual conditions. Those conditions remain hypothetical. At this layer, the question of past travel becomes grounded in the substance of the universe. It is not enough for equations to admit a strange path. Nature must supply matter and energy able to make the path real, stable, and passable. Known positive energy matter bends space-time without opening a controllable past. Limited quantum negative energy exists only under constrained conditions, and not as a practical reservoir. Extreme gravity slows time and traps light, but does not offer a safe return to earlier events. The material requirements remain beyond observed physics. The past may have a place in space-time descriptions, yet no known form of matter provides the support needed to turn that place into a road. Within the search for impossible materials, one proposed structure draws attention more than most others. It is the wormhole, a hypothetical passage connecting two separated regions of space-time. The word suggests a tunnel, but the scientific idea is more precise. A wormhole is a geometry in which two mouths are joined by a throat, so that a path through the throat could connect distant places more directly than an ordinary route through outside space. In some mathematical descriptions, the two mouths might also be separated in time. This is why wormholes enter discussions of travel to the past. They seem to offer a shortcut not only across space, but possibly across the order of events. The simplest wormholes appear in idealized solutions of general relativity. These early forms are not useful passages. They close too quickly, or they contain horizons that trap anything entering, or they lead into regions that cannot be crossed safely. A traversable wormhole, meaning one that matter or signals could pass through in both directions, requires far more special conditions. The throat must remain open. Tidal forces, which stretch and squeeze objects because gravity differs from one place to another, must not destroy anything passing through. The geometry must remain stable when light, particles, and disturbances enter. These requirements are severe. They turn the wormhole from a simple image into a demanding physical problem. A wormhole becomes related to past travel when its two mouths experience time differently. If one mouth is moved at very high speed and then brought back, or if it is placed in a stronger gravitational field for a while, time can pass at a different rate for that mouth compared with the other. This is ordinary time dilation applied to the mouths of a hypothetical passage, if the wormhole throat still connects them. A traveller entering one mouth might emerge from the other at a time that is earlier relative to the outside world. In this way, the wormhole could become a time machine in theory. The concept depends on joining a shortcut through space-time with the flexible timing allowed by relativity. This reasoning is careful, but it rests on a structure not known to exist. No traversable wormhole has been observed. Astronomers see objects whose gravity bends light, and they see compact regions consistent with black holes. These are not confirmed wormhole mouths. A wormhole might imitate some gravitational effects in theory, but no evidence shows a stable throat connecting distant regions. The absence of evidence does not prove that no wormholes exist anywhere, but it means they remain hypothetical. A scientific proposal must be judged not only by mathematical elegance, but also by observation, stability, and compatibility with known matter. On those grounds, traversable wormholes remain unconfirmed. The throat of a traversable wormhole is the central difficulty. Gravity tends to make matter attract and space-time close inward under many conditions. To hold a throat open, many models require exotic matter with negative energy density. This is the same difficulty found in the deeper material layer. Ordinary matter would tend to collapse the passage or form a horizon. Negative energy could, in some equations, push in the required way to keep the throat open. Yet known negative energy effects are small and constrained. They do not provide a clear method for building or maintaining a human scale or signal scale passage. The wormhole depends on a resource that physics has not shown how to supply in usable form. Even if such a throat existed, passing through it would not be simple. The traveller's energy would affect the geometry. Radiation entering the wormhole could accumulate. Quantum fields near the throat could behave in ways that destabilize the passage. Small imperfections might grow. A wormhole arranged to create a time difference between its mouths could be especially vulnerable. Signals might loop through the wormhole and return repeatedly, building energy near the moment when past-directed paths become possible. Some studies suggest that this feedback could destroy the wormhole or prevent the time machine region from forming. A full answer likely requires quantum gravity, a theory combining gravity and quantum physics that is not yet complete. There is also the question of formation. A wormhole cannot simply be assumed as a finished tunnel. A physical account must explain how it comes into being. It might be imagined as a relic from the early universe, when space-time was hot, dense, and rapidly changing. It might be imagined as engineered by an advanced civilization. Both ideas face the same gap. No observed process is known to create a traversable wormhole. No method is known for enlarging a microscopic wormhole if such things exist. No method is known for transporting, stabilizing, or timing its mouths. The geometry may be written in equations, but the universe has not supplied the process that turns the equation into a working object. A black hole is sometimes confused with a wormhole because some mathematical extensions of black hole solutions contain bridge-like structures. These bridges do not provide practical paths into the past. They are not stable doors for travelers. The event horizon prevents outward escape once crossed in the ordinary black hole region, and the internal structure involves extreme curvature, singularities in classical theory, and conditions beyond safe passage. A singularity is a place where classical general relativity predicts quantities such as density or curvature become infinite, signaling that the theory is no longer adequate there. The presence of such mathematical features does not mean a route is available. It means the description reaches its limit. Wormholes also show why shortcuts are not the same as freedom from causality. A spatial shortcut could, in principle, allow rapid travel between distant places without locally exceeding the speed of light. But if the shortcut combines with time dilation in the wrong way, it can create a closed, time-like curve. Then the same causality problems return. A traveller or signal could emerge early enough to influence its own departure. The wormhole has not removed the paradox. It has given the paradox a geometric shape. Any physical theory allowing such a structure must also explain how consistency is preserved, or why the structure cannot form in realistic conditions. The known universe is full of natural shortcuts in a gentler sense. Light follows curved paths around galaxies. Gravity lenses the images of distant objects. Cosmic expansion stretches distances between galaxy clusters. Stars and planets follow geodesics, which are natural paths through curved space-time. None of these creates a traversable throat into another time. They show that space-time is active and shaped by mass and energy. They do not show that it can be folded into a stable tunnel that carries matter into the past. The observed cosmos is rich in curvature but conservative in causal order. At this layer, the wormhole becomes a clear example of the difference between a scientific possibility in equations and a physical possibility in nature. It is not dismissed because it sounds strange. It is examined because general relativity allows unusual geometries under certain assumptions. Yet each assumption must be paid for with matter, energy, stability, formation, and observation. The payments are not known to be possible. A traversable wormhole would need an open throat, controlled time differences, safe passage, and protection from quantum and gravitational collapse. No known object meets these conditions. The idea remains valuable as a test of the boundaries of theory, but it does not provide a demonstrated road to the past. The inward movement therefore leaves the tunnel image behind and keeps the physical lesson. A passage through space-time is not created by naming it. It must be supported by lawful structure. It must survive the presence of the traveller. It must avoid turning information and cause into contradiction. Wormholes show how relativity can imagine strange connections, and they also show how strongly nature resists turning those connections into usable past travel. The past, even if it has a place in space-time, remains separated by more than distance. It is separated by the conditions that determine which paths can exist, which signals can pass, and which geometries the universe can actually hold. Beneath the geometry of wormholes lies the smaller and less visible layer of quantum physics. Quantum physics describes matter and energy at scales where particles, fields, and probabilities become essential. It does not replace relativity in ordinary large-scale motion, but it reveals that the deep structure of nature is not built from tiny solid grains following simple paths in the old sense. Electrons, photons, atoms, and fields behave according to rules that allow uncertainty, wave-like behavior, and probabilistic outcomes. Because quantum physics already unsettles ordinary intuition, it is often pulled into hopes about travelling to the past. Yet the quantum layer does not remove the causal boundary. It makes the boundary more subtle. One of the best-known quantum ideas is uncertainty. This does not mean that anything can happen without limit. It means that certain pairs of physical properties, such as position and momentum, cannot both be given exact values at the same time in the same way. Momentum is related to mass and motion. The more precisely one property is defined, the less precisely the paired property can be defined. This is not caused by poor instruments. It belongs to the state of the system itself. Uncertainty allows microscopic systems to behave in ways that differ from everyday objects, but it does not allow a person, a machine, or a message to choose an earlier time and arrive there with controllable intent. Quantum systems are described by wave functions, mathematical objects used to calculate probabilities for possible measurements. Before measurement, a system may be in a superposition, meaning a combination of possible states rather than one ordinary state. When a measurement occurs, a definite outcome is recorded. Different interpretations explain this process in different ways, and some remain matters of debate. The predictions, however, are clear and repeatedly tested. Superposition is real in the sense that it affects interference, atomic structure, lasers, and many modern technologies. It is not the same as a doorway through time. A particle in a superposition is not a traveller freely moving between yesterday and tomorrow. It is a quantum system whose possible outcomes follow strict mathematical rules. Entanglement is another idea often mistaken for a time machine. Entanglement occurs when two or more quantum systems share a state so that measurements on them are correlated, even when they are far apart. Experiments show that these correlations cannot be explained by simple hidden instructions carried locally in the old classical way. This is one of the most profound results in physics, yet entanglement does not permit controllable faster-than-light communication. A measurement outcome cannot be chosen freely to send a message to the other particle. The correlations become meaningful only when ordinary information is later compared through normal channels. Since those channels obey the speed of light, entanglement does not allow a signal to reach the past. Quantum field theory brings the small layer closer to space-time. In this theory, particles are excitations of fields that fill space. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. Empty space is not simple nothing. It has a quantum structure with fluctuations, meaning temporary variations in field values. These fluctuations can have measurable effects, but they are not free energy stores or hidden tunnels. They follow conservation rules and mathematical constraints. Some effects can produce local negative energy density for short periods or small regions, yet these effects are limited. They do not become large. Stable reservoirs capable of holding open a wormhole or making a usable loop in time. Quantum theory also treats information with care. Information is physical because it must be stored in states of matter or fields. A bit in a computer, a spin in a particle, a mark on paper, and a memory in a brain all require physical arrangements. Quantum information can be delicate. It can be changed by measurement, disturbed by the environment, and protected only through careful isolation or error correction. These features do not make information independent of time. They make its handling more constrained. A message into the past would still need a physical carrier and a causal path. Quantum theory provides no known method for sending a chosen message into an earlier event where it can alter its own cause. Some theoretical studies ask how quantum systems would behave near closed time-like curves if such curves existed. These studies are useful because they test the consistency of the theory under strange conditions. Some models impose self-consistency, so only histories without contradiction are allowed. Other models explore how quantum probabilities might behave if a system interacted with its own past. These are not demonstrations that closed time-like curves exist. They are controlled mathematical investigations of what would follow under assumptions not known to be realized in nature. The difference matters. A calculation can reveal the consequences of a hypothetical path without proving that the universe contains that path. Quantum gravity remains the deeper unknown. General relativity describes gravity and spacetime very well at large scales. Quantum physics describes matter and fields very well at small scales. A complete theory of quantum gravity would explain situations where both are essential, such as the earliest universe, the centers of black holes, and perhaps the formation or prevention of time loops. No complete experimentally confirmed theory of quantum gravity exists. Several approaches are studied, including string theory, loop quantum gravity, and other frameworks. They offer insights, but none has produced a verified machine for past travel. Where knowledge is incomplete, careful science states the uncertainty without turning it into permission for speculation. One possibility is that quantum effects protect chronology. Near the formation of a region where closed time-like curves might appear, quantum fields could become highly energetic. Their energy might curve space-time in a way that prevents the region from forming. This idea is not fully proven because the necessary calculations require physics beyond current complete knowledge. Still, it matches the broader pattern seen in nature. Whenever past-directed signals seem possible in a rough description, deeper analysis often restores causal order or removes controllable signaling. Observations so far show no violation of causality in quantum experiments, even in those that reveal strong non-classical behavior. Quantum tunneling is another process sometimes misread. Tunneling occurs when a particle has a probability of being found beyond a barrier that classical physics would not allow it to cross. This effect is real and important in nuclear fusion, radioactive decay, and electronic devices. But tunneling is not a macroscopic escape from time. It does not allow a human body to pass through years. It does not send a signal into the past. It is a probabilistic process governed by the wave nature of particles and the structure of energy barriers. The particle's detection still occurs in the forward order of measurement and record. The quantum layer therefore narrows the hope rather than expanding it. It shows that nature is not limited to the simple pictures of everyday motion. It allows uncertainty, superposition, entanglement, fluctuations, and tunneling. These features make the universe deeper and less mechanical than older models suggested, yet they do not give controllable access to earlier events. They do not let information outrun causality in a usable way. They do not provide the stable negative energy or complete spacetime control required by wormhole time machines. The small-scale world is strange, but its strangeness is lawful. It changes the texture of reality without opening the past as a place to enter. Below quantum limits lies a quieter boundary that appears in every warm room, every cooling stone, every living body, and every cloud of gas. This boundary is the thermodynamic arrow of time. Thermodynamics is the science of heat, energy, and the large-scale behavior of many particles. Its arrow points from lower entropy toward higher entropy in ordinary closed systems. Entropy is a measure connected to the number of microscopic arrangements that can produce the same visible state. A state with low entropy has fewer possible arrangements. A state with high entropy has many more. The idea can sound abstract, but its signs are familiar. Heat spreads, perfume disperses, ice melts in warm air, dust settles unevenly. Mixed things do not usually unmix by themselves. This arrow does not come from a single particle deciding to move forward in time. At the smallest level, many physical laws work almost the same if time is reversed. A movie of two ideal particles colliding could often look physically possible when played backward. The difficulty appears when countless particles are involved. A cup of hot liquid contains an enormous number of molecules moving in many ways. The heat spreads into the cup, the table, and the air because there are vastly more microscopic arrangements in which energy is shared than arrangements in which it remains neatly concentrated. The forward direction is therefore statistical. It arises from probability across immense numbers of parts. The statistical nature does not make the arrow weak in daily life. For large systems, the numbers are so enormous that reversal becomes effectively impossible. It is not forbidden for every molecule in a room to gather suddenly into one corner, leaving the rest of the room empty, but the probability is so small that it has no practical meaning in ordinary physical reality. A shattered glass could be described, particle by particle, in a reversed motion that returns shards to the table and lifts them into a whole cup, but arranging the exact motion of every fragment, air molecule, sound wave, and heat transfer would require control beyond known possibility. The world moves toward more probable arrangements, and those arrangements define the lived direction of time. This arrow gives the past its distinctive texture. The past is a region of lower entropy relative to many present records. A footprint forms when sand is compressed. A fossil forms when an organism is buried and minerals slowly replace or preserve structure. A memory forms when the brain is physically changed by experience. Each record is produced by an irreversible process. Energy is used. Heat is released. Matter is rearranged. The record points backward because its formation required an earlier cause. A footprint does not normally appear before a foot presses the ground. A memory does not form before the event that shapes it. The thermodynamic arrow supports the causal arrow by making records stable in one direction. Living systems do not escape this arrow. A body maintains order by taking in energy and matter, then releasing heat and waste into the surroundings. Cells build proteins, repair membranes, copy genetic material, and maintain chemical gradients. These local pockets of order are possible because the larger environment gains entropy. Life is not a violation of thermodynamics. It is a process that uses flows of energy to hold structure for a time. Aging, healing, growth, and decay all occur within this energy flow. A body cannot simply reverse into an earlier age by retracing a path through time. To undo aging completely would require reversing countless molecular changes, restoring lost arrangements, removing accumulated damage, and coordinating the surrounding environment as well. The thermodynamic arrow also affects machines. A clock works by using ordered physical processes, but it produces heat and suffers wear. A computer stores information, but it consumes energy and must manage waste heat. A spacecraft moves through space, but its engines burn fuel, radiate energy, and change their environment. Any proposed machine for reaching the past would have to operate inside this same arrow. It could not be a perfect symbol outside heat and disorder. It would have to preserve its structure, power its fields, control radiation, and protect information. Each operation would produce consequences that point forward thermodynamically. The machine itself would age while trying to undo the order of time around it. A full reversal of the thermodynamic arrow would require more than moving an object backward along a path. It would require changing the microscopic state of the object and its environment in an extraordinarily precise way. Every molecule in the traveller's body, every photon emitted, every vibration in the walls, every trace of heat, and every record of the departure would need to be coordinated. Otherwise, the traveller would carry forward-made records into a supposedly earlier state. The mismatch would reveal the direction. A person arriving in the past with memories from the future would be a thermodynamic object shaped by later events. The body would contain traces of a history that had not yet occurred in the surrounding world. This shows why reversing time is not the same as travelling through time. A reversed film can make smoke gather into a candle, or waves lift a fallen stone back into a hand. But the film is only an image, and the reversal is imposed by an outside viewer. The actual physical reversal would require every microscopic motion to be inverted with perfect accuracy. Even the light carrying the image, the camera sensor, the air, and the heat generated by the process would belong to a larger system. There is no outside hand in the universe known to physics that rewinds all particles while leaving a traveller free to observe the process. The observer is part of the system, and would be reversed too. Entropy also explains why the past is knowable while the future is not fixed in the same practical way. Records accumulate from earlier events. They are stored in durable structures. From these records, scientists reconstruct prior states. The future has fewer records because it has not yet produced them along the observer's world line. There may be laws that constrain future evolution, and in some systems predictions can be highly accurate. Still, the practical asymmetry remains. There are fossils of old organisms, but no fossils of future ones. There are photographs of earlier skies, but not of skies that have not yet sent light to the camera. Entropy gives records their direction. In cosmology, the thermodynamic arrow reaches back to the early universe. Observations indicate that the early universe was hot, dense, and remarkably smooth on large scales, a condition with low gravitational entropy compared with later cosmic structure. Over time, matter clumps into stars, galaxies, black holes, and wider webs under gravity. This growth of structure is part of the universe's thermodynamic history. The details are complex, especially because gravity behaves differently from gas in a box. But the overall arrow remains clear. The present universe contains records of earlier states because it evolved from conditions that allowed records to form forward. Why the early universe had such a low entropy beginning remains a deep question in physics. This layer makes past travel difficult in a more intimate way. Even if space-time geometry allowed a loop, the traveller would still be a thermodynamic system. The journey would involve heat, information, memory, and irreversible change. A loop into the past would need to fit these processes into a consistent whole. It would need to explain how entropy behaves around the loop, how records avoid contradiction, and how matter does not carry impossible histories. Known physics gives no practical method for arranging such a state. The arrow of entropy does not shout, it simply appears everywhere, in every warmed surface and every fading trace, showing that the world's records form from earlier to later. Inside the thermodynamic arrow, the next layer is information and memory. The past reaches the present through records, and every record is physical. A memory in a brain, a mark in stone, a layer in ice, a ring in a tree, a signal in a computer, and a pattern of light on a sensor all depend on matter arranged in a particular way. Information is not a ghost floating outside the world. It is carried by physical states that can be changed, copied, damaged, and erased. This makes the past seem near, because its traces are everywhere. It also shows why nearness is not access. A record is a present structure shaped by an earlier event, not the earlier event itself. A memory forms when experience changes the nervous system. Light enters the eyes, sound reaches the ears, pressure touches skin, and chemical signals pass through the body. The brain responds by altering patterns of activity and connection. Later, part of that pattern can be reactivated, creating remembrance. The remembered scene may feel vivid, but it is not the original scene restored. It is a present act of reconstruction. It depends on the living brain at the later time. It can be incomplete, softened, blended, or changed by later experience. This does not make memory useless. It makes memory a record, and records always belong to the time in which they exist. Written records work in a similar way, though they seem more stable. Ink on paper, carved stone, magnetic storage, and digital memory all hold information by arranging matter into durable patterns. A written sentence remains because pigment, fiber, or electronic states preserve differences that can be read later. The information points back toward a writer, a tool, a language, and a moment of inscription. Yet the page is present matter. It does not contain the earlier room, the earlier hand, or the earlier air. It contains a pattern produced by them. Reading the page is an interaction in the present with a structure inherited from the past. Nature keeps records without intention. Tree rings form as growth changes with seasons and environmental conditions. Ice cores preserve layers of snowfall, trapped air, dust, and chemical traces. Sedimentary rocks hold grains laid down in water, wind, or ice. Fossils preserve shapes and sometimes microscopic details from organisms that lived long before human observers. Craters record impacts. River valleys record erosion. These records allow scientists to reconstruct past climates, landscapes, and biological change. The reconstruction is careful because each record is partial. A layer can be disturbed, a fossil can be rare, a chemical signal can have several causes. Still, the direction remains steady. Earlier events shape later structures that can be studied. Light is another record. A photograph forms when photons alter a sensor or film. A telescope image forms when old light is collected and measured. A spectrum records the wavelengths present in incoming radiation, carrying signs of temperature, motion, and chemical composition. The information arrives after the event that produced it. This delay is what makes observation possible. The signal travels forward, reaches the instrument, and becomes a new record. The record may then be stored, copied, compared, and interpreted. At no point does the process require the observer to enter the earlier event. It only requires that the earlier event leave a signal capable of surviving the journey. Information also depends on erasure. A notebook can be burned, a computer file can be overwritten, a memory can fade, a fossil can be destroyed by heat and pressure. When a record disappears, the past event does not change, but access to that evidence is reduced. This distinction matters. The past is not made real by every record that survives, and it is not made unreal by records that vanish. Records are the bridges of knowledge, not the source of the event itself. They give later systems a way to infer earlier states. They do not reopen those states. The link between information and entropy is deep. Creating a reliable record usually means establishing a stable difference between possible states. A mark is present rather than absent. A bit is one state rather than another. A groove, layer, or chemical ratio carries a pattern. Making and maintaining such differences requires physical work and usually releases heat into the surroundings. Erasing information also has thermodynamic cost in many contexts. Because reducing stored distinctions changes the physical state of a system. Information is therefore tied to energy, matter, and time's direction. It is not a free passage across history. It is a structured trace produced by irreversible processes. Past travel would disturb this arrangement because a traveller carries records. A person arriving in an earlier time would bring memories, biological age, learned skills, scars, written notes, devices, and perhaps stored data. These records would have been formed by events that, from the earlier time's viewpoint, had not occurred. The traveller would become a pocket of later information inside an earlier environment. If that information affects events, the chain of cause becomes circular. If it cannot affect events, then the journey becomes part of a fixed history rather than an open return. In both cases, the ordinary meaning of memory changes. A memory would no longer simply point backward along the traveller's world line in the same direction as the surrounding world's records. Some physical systems can store information for extremely long times. Ancient minerals can preserve magnetic orientations from earlier fields. DNA can survive for limited spans under favourable conditions, though it breaks down over time. Light from distant galaxies can travel for billions of years before detection. These examples show that records can be durable, but durability is not timelessness. Every record changes with its carrier. It may decay slowly, be transformed, or become harder to read. Its survival depends on physical conditions. Even the most ancient signal arrives as present energy in an instrument. The past is carried forward by fragile or durable messengers, not held open as a chamber. At this layer, the idea that the past still exists becomes more precise. The past exists for present knowledge through records and traces. It exists in the structure of space-time for theories that treat events as part of a four-dimensional whole. It exists in causes that have shaped current matter, but none of these meanings grants direct return. A record is not a doorway. A memory is not a machine. A fossil is not the living animal restored. A beam of old light is not the star's old surface waiting to be touched. Information gives the past presence without giving it availability. The inner lesson is calm and restrained. Everything known about earlier time comes through present states shaped by lawful processes. The more records survive, the clearer the reconstruction becomes. The fewer records survive, the more uncertainty remains. Science respects this by comparing evidence, testing models, and separating what observations indicate from what remains unknown. Past travel would require more than better records. It would require a path that carries matter and information into the earlier causes of those records. Known physics provides no such path. The past speaks through memory, stone, light, ice, and written marks. It does not answer by becoming a place that can be entered again. Inside information and memory lies the deeper boundary where the main theories of physics meet without yet becoming one complete account. This boundary is not a wall in space. It is the edge of present understanding, where relativity, quantum physics, thermodynamics, and causality all touch the question of time. Each theory works with great accuracy in its own tested range. Relativity describes space-time, gravity, motion, and the bending of light. Quantum physics describes particles, fields, uncertainty, and microscopic interactions. Thermodynamics describes heat, entropy, and the formation of records. Causality holds the order by which influences move from earlier to later events. Past travel presses against all of them at once. General relativity gives time a geometric role. It allows space-time to curve and stretch. It allows clocks to tick at different rates in different conditions. It allows black holes, gravitational waves, expanding cosmic space, and the bending of starlight. Its equations can also contain unusual solutions when matter and energy are arranged in special ways. Some of these solutions contain paths that loop through time. Yet the existence of an equation is not the same as the existence of a stable region in nature. The equation must be joined to realistic sources, boundary conditions, and physical processes. Boundary conditions are the limits and starting arrangements needed to define a system. Without them, a mathematical shape can float free from the universe it is meant to describe. Quantum physics brings a different kind of restraint. It does not treat empty space as an empty stage. It fills space with fields that fluctuate and respond. It limits how precisely certain properties can be fixed. It allows correlations stronger than classical expectations. It also preserves the rule that controllable signals do not move faster than light. When quantum fields are placed near extreme space-time shapes, their behavior can become difficult to calculate. A region that seems harmless in classical relativity may become unstable when quantum effects are included. This is one reason past travel remains uncertain at the deepest level. The theory that might decide the matter fully is not yet complete. The missing theory is often called quantum gravity. It would describe gravity according to quantum principles while also preserving what relativity has shown about space-time. Such a theory is needed where gravity becomes extremely strong and distances become extremely small, as in the early universe or near the center of a black hole in classical descriptions. It may also be needed to understand whether space-time can form closed time loops, or whether quantum effects prevent them. Current approaches offer possible structures, but observations have not yet selected a final theory. The lack of a complete theory does not mean that every imagined possibility is open. It means that careful limits must be stated. Known physics does not provide a working path to the past. An unknown physics cannot be used as proof that such a path exists. Causality sits at this boundary as both a principle and a pattern of observation. Experiments in particle physics, astronomy, and quantum information show no controlled violation of causal order. Signals are not observed arriving before they are sent. Records do not appear before the events that make them. Effects do not erase their own causes in laboratories or in the sky. This regularity is so deep that it is often assumed in the structure of theories themselves. Equations are written so that systems evolve from one state to another in a consistent way. Measurements are interpreted as later records of earlier interactions. If past travel were possible, it would need to fit within this structure or replace it with something equally consistent. Thermodynamics adds another demand. A time loop would have to handle entropy. It would need to explain how heat, disorder, aging, memory, and information behave along a path that returns to an earlier region. A traveller cannot be treated as a point without temperature or history. The traveller carries a body, a machine, or a signal. Each has internal states, energy flows, and records. If the path loops, these states must remain consistent around the loop. A notebook cannot be both worn by use and newly created without an account of the wear. A memory cannot arise from a future event and still serve as an ordinary record without making the chain circular. The inner boundary is therefore not only about space-time shape. It is also about the physical content carried through that shape. Some ideas try to protect consistency by making time loops self-consistent. In such a universe, anything that happens in the past because of a traveller has always been part of the past. Contradiction is avoided because events cannot unfold otherwise. This kind of model may be logically arranged, but it changes the meaning of intervention. The traveller does not alter history. The traveller completes it. The model also leaves open the problem of how the loop forms and how matter and energy remain stable. Self-consistency may remove one contradiction while leaving many physical demands unanswered. It is a rule for allowed histories, not evidence that the universe contains those histories. Other ideas try to avoid contradiction by separating histories. In such views, action in an earlier region would not change the original history, but would relate to another branch or state. These ideas are not established mechanisms for travel. Quantum interpretations that involve branching are designed to explain measurement outcomes, not to give macroscopic objects a route into selected earlier worlds. They do not remove the need for a physical path, energy support, and causal account. They also do not show how a traveller could choose a branch or verify a return to an earlier cause. The problem remains grounded in physical connection, not only in logical arrangement. At this depth, language itself can mislead. To say that the past still exists may mean that it is part of space-time. It may mean that records of it remain. It may mean that laws allow it to be described from present evidence. These meanings are different. None automatically means that the past is a place available for entry. A city can be distant and reachable because a path through space connects to its present state. A past event can be real in a space-time description and still unreachable because no allowed world line connects the traveller to it from the traveller's later state. The inner boundary is partly a boundary between meanings. The same caution applies to possibility. In science, possible can mean not logically contradictory, allowed by a simplified equation, not yet ruled out by observation, or physically realizable under known conditions. These are not the same. Past travel may appear in a mathematical solution under special assumptions. It may remain unproven impossible in every future theory. Yet it is not physically realized by any known process. It is not supported by known materials. It is not observed in nature. It is not produced in experiments. The strongest statement that consensus physics supports is modest. Time dilation is real. Looking back through light is real. Records of the past are real. Travel into the past is not known to be possible. This inner layer does not end in despair or certainty beyond evidence. It ends in careful restraint. The laws that work so well across the universe protect order at every tested scale. They allow a rich past to be studied through light, stone, memory, and motion. They allow time to stretch and gravity to shape duration. They allow microscopic uncertainty without permitting controllable messages into yesterday. Where theories are incomplete, the unknown remains unknown. It is not a hidden permission slip. The edge of knowledge is real, but it is not empty. It is lined by everything already measured, and those measurements point toward a universe where the past can be known, described, and carried as record, but not entered again. At the innermost practical layer, what remains possible is clear and limited. Time can stretch. Clocks can disagree. Light can bring images from long ago. Gravity can slow the rate of change measured between different places. Motion can make one path through space-time shorter in elapsed time than another. These effects are real, tested, and important. They show that time is not the simple universal flow imagined in everyday life. They also show that flexibility is not the same as reversal. Known physics allows different passages into the future and deep observation of the past. It does not provide a verified way for matter, memory, or messages to enter an earlier event and act there. The most established form of time travel is travel toward the future by unequal aging. A person moving very fast, or spending time in stronger gravity, can experience less elapsed time than another person elsewhere. This is not a leap outside the universe. It is a path through space-time with a different amount of proper time. The traveller's body still changes in the usual sequence. Cells continue their chemistry. Thoughts follow earlier thoughts. A clock carried by the traveller ticks forward. When the traveller meets others again, their clocks may show more elapsed time. In this sense, the traveller reaches a later world while having aged less. The effect is real, but it is not a return to the past. The second established connection to the past is observation. The universe is filled with old light and old traces. A telescope receives radiation from stars and galaxies as they were when the light began its journey. A detector measures particles that have crossed space. A rock records pressure, heat, and chemical change. Ice preserves air from earlier climates. Living bodies carry inherited molecules shaped by long biological history. These records allow the past to be studied with care. They are not illusions. They are physical evidence. Yet the act of receiving a signal or reading a record occurs in the present. The past is known through what it sends forward, not through a door that opens backward. The third established fact is that space-time can be described as a four-dimensional structure. Events have positions in space and time. Different observers may divide that structure into past, present, and future in different ways when distant events are involved. This makes the past more subtle than a vanished nothing. It may be treated as part of the complete structure of events, but a structure is not the same as a transport system. To reach a point in space-time, an object needs an allowed world line. The world line must be continuous, physical, and compatible with local laws, known world lines for matter move forward within light cones. They do not bend naturally into earlier parts of their own history. The fourth established fact is that causality remains intact in every tested setting. Causes leave effects, signals travel at finite speeds, records form after the events they record. Quantum experiments reveal deep correlations, but they do not allow controllable messages into the past. Relativity changes simultaneity across distance, but it preserves the order of causally connected events. Thermodynamics gives records a direction through entropy. Together, these facts form a steady pattern. The universe permits complexity, delay, curvature, uncertainty, and uneven aging. It does not show effects freely rewriting their causes. Theoretical ideas about past travel remain useful as boundary tests. Wormholes, closed time-like curves, rotating spacetimes, and quantum models with self-consistency help physicists ask how far known theories can be stretched. They reveal where equations allow strange shapes and where matter, energy, stability, and causality become difficult. These ideas are not the same as engineering plans. A traversable wormhole has not been observed. Exotic matter in the required form has not been found. Stable time loops have not been produced. No experiment sends a usable signal before its own transmission. These limits do not come from a lack of imagination. They come from what nature has shown so far. The phrase, even if it still exists, therefore needs careful meaning. The past may still exist as part of a space-time description. It certainly exists as cause, record, structure, and memory in the present. It exists in light still travelling, in rocks still layered, in atoms still arranged by earlier events, and in the minds and instruments that carry traces. But existence in these senses does not imply accessibility. A fossil is a present object, not the living animal. Ancient light is a present signal, not the old star restored. A memory is a present brain state, not a reopened moment. The past is deeply present through consequences, while remaining closed as a destination. This distinction gives the final answer its calm shape. The inability to travel to the past is not caused by one simple barrier that might be broken like a wall. It arises from many connected layers. Light carries information forward. World lines preserve local order. Causality protects cause and effect. Entropy gives records their direction. Matter and energy do not provide the required space-time structures. Quantum physics does not supply controllable backward signals. Relativity makes time flexible but not freely reversible. Each layer is different, yet they all point toward the same result. The past can be approached by evidence and understood through theory, but not entered by known physical means. There is still room for humility. Physics is not complete. Quantum gravity remains unfinished. The earliest universe and the interiors of black holes still contain unresolved questions. Some mathematical possibilities are not fully ruled out in every conceivable setting. Careful science leaves those uncertainties in place. It does not turn them into claims of practical travel. What is known remains strong enough to guide the answer. Every observation and experiment so far supports a universe where time has flexible rates, delayed signals, and durable records, but where the causal order of events is not open to casual reversal. The final inward view is therefore quiet. The past is not simply gone, because it has shaped everything that exists now. It is present in the sky as old light, in earth as stone memory, in life as inheritance, and in thought as record. It is also not waiting like a room behind a closed door. It belongs to the structure and history of the universe. but the traveller belongs to a forward-moving path within that same structure. Known physics allows the path to bend in duration, not to turn back into its own origin. The past remains knowable, meaningful, and real in its traces, while staying unreachable as a place to stand again. The mind grows quiet as the layers settle into place. Time is no longer only the ticking of a clock or the turning of a page. It becomes a pattern that holds change, a structure that carries every event, a direction that shapes every record. The past rests within this pattern as cause and trace, not as a corridor that can be walked again. Light arrives from distant stars, carrying moments that have already passed. Stones hold pressure and heat from earlier ages. Bodies carry marks of growth and memory. Each sign is gentle, each sign is real, and each sign moves forward into the present. Nothing in this calm arrangement needs to be forced. The universe allows its history to be read without reopening it. It allows time to stretch, to slow, to differ between paths, while still keeping the quiet order of cause before effect. The deeper the view becomes, the more the same boundary appears in different forms. Geometry holds paths in place. Energy shapes what can exist. Entropy gives direction to change. Information lives in present matter, pointing back without returning. These are not barriers placed from outside. They are the ordinary ways the world holds together. The idea of returning to the past softens into something else. It becomes the steady act of understanding what has already shaped the present. It becomes the patient reading of signals, the careful study of records, the quiet tracing of causes. The past is not empty. It is carried forward in every structure and every motion. It is present without being open. The path continues onward, not as a loss, but as the only direction in which change can be lived,